Thank you very much. Let me first thank the organizers for organizing such a nice conference. In this talk, I would like to explain a possible way how to generalize one complex function theory to higher dimensions. I shall talk about the so-called generalized Cauchy-Riemann equations Stein and Weis introduced a long time ago. In the second part of this talk, I give some new results on homogeneous solutions of this system of equations, but only in dimension 4. This is a joint work with Fred Brax, Henny Deschepper, Vladimir Souček, and Wei Wang. Let me start with a short motivation coming from physics. In particle physics, the field equations in the Minkowski spacetime for massless particles of lower spins play a fundamental role. Namely, for spin 0, the wave equation, for spin 1/2, the Dirac, or better to say, massless neutrino equation, for spin 1, the Maxwell equations, for spin 3/2, the Rarita-Schwinger equation, and for spin 2, the equation of the linearized gravity. Actually, for any spin, Roger Penrose initiated his twistor program, a systematic study of solutions of massless field equations. In mathematics, complex analysis, function theory of one complex variable studies solutions of the Cauchy-Riemann equations in the complex plane, and of course the complex analysis is very important theory for many fields of mathematics, and from the beginning a natural question has arisen what is how this important and deeper theory can be generalized to higher dimensions. Of course, one possibility is to study several complex variables, but there is less known possibility, and it is to develop a function theory of one hypercomplex variable of the Euclidean space Rm. Hypercomplex analysis was first studied by Swiss mathematician Fieter in 30s in dimension 4 using the quaternions, and since 70s Richard Delange studied hypercomplex analysis in any dimension, and this theory studies solutions of the Dirac equation in the Euclidean space Rm, or in other words, studies massless fields of spin 1/2 in Rm. Even after 50 years, this research area is still very active and full of new results, but recently there has been a growing interest in massless fields of any spin, not just spin 1/2. So we want to build higher spin hypercomplex analysis, and there are several properties higher spin hypercomplex analysis should have, and the first is that the underlying symmetry should be the group spin M, the universal cover of the group SOM of rotations of the Euclidean space Rm. For an arbitrary irreducible representation, V of spin M, it should study solutions of massless field equations defined in Rm and V-valued. And for basic spinor representations, we should get the classical hypercomplex analysis. This is clear, but it is not so clear, at least for a general irreducible representation, what are the right massless field equations. One possibility is to use the so-called higher spin Dirac operators, as in this paper. But there is a second possibility, and it is to take as massless field equations the generalized Cauchy-Riemann equations Stein and Weis introduced and studied already in 1968. And in this talk, we take this second possibility. In this Stein's and Weis paper, they described a systematic construction of first order rotationally invariant differential operators. So let us describe this construction briefly. We consider an irreducible spin module V and its tensor product with the defining representation Cm. It decomposes into irreducible pieces F0 up to Fr, and F0 is the Cartan product of V and Cm. It's a unique irreducible submodule with the highest weight equal to the sum of highest weights of V and Cm. And we denote by J the projection of this tensor product onto the corresponding piece Fj. Then for each J, we define the Stein-Weis gradient dj as the composition of this projection by J with the gradient. By this construction, each Stein-Weis gradient dj is rotationally invariant, but it is known that these operators are even conformally invariant, and this construction can be generalized to much broader framework, parabolic geometries, but in this talk we are interested just in the flat Euclidean case. Examples of Stein-Weis gradients is the Dirac operator itself and higher spin Dirac operators. Let, for simplicity, assume that our dimension M is even. Then we have two basic spinor representations, S plus minus, with the highest weights with all terms 1/2, and with the last term plus or minus 1/2. The tensor product of basic spinor representation with the defining representation has two pieces. The Cartan product and the other basic spinor representation, and the Stein-Weis gradient corresponding to this second piece is nothing else than the Dirac operator. This construction, this example can be generalized in the following way. Let V lambda plus minus be an irreducible spin module with highest weights lambda plus minus with arbitrary first and minus one terms, and with the last term plus or minus 1/2. Then the tensor product with the defining representation contains the piece with the highest weight with the opposite sign. So we have the corresponding Stein-Weis gradient. Corresponding Stein-Weis gradient we call higher spin Dirac operator, and it is known that this operator is unique, conformally invariant elliptic first order differential operator. And basic results of function theory for higher spin Dirac operators were given in this paper. Let us now introduce the generalized Cauchy-Riemann equations. For an irreducible spin module V, we have decomposition of this tensor product, where the first piece is the Cartan product, and to each Fj, piece Fj, we have the corresponding Stein-Weis gradient dj. Then we define the generalized Cauchy-Riemann equations as the homogeneous system for all Stein-Weis gradients, except for that corresponding to the Cartan product. For basic spinor representations, the generalized Cauchy-Riemann equations are nothing else than the Dirac equation itself, so nothing new, but let us consider lambda s, the s antisymmetric power of the defining representation, Cm, then its tensor product with the defining representation has three pieces. The Cartan product, lambda to s plus 1 and lambda to s minus 1, and the Stein-Weis gradient corresponding to the second piece is just the Ram differential, and to the last piece is its codifferential. So in this case, the generalized Cauchy-Riemann equations is the Hodge-de-Ram system for D and D star. So in general, the generalized Cauchy-Riemann equations are not conformally invariant nor elliptic as for higher spin Dirac operators. In the rest of this talk, I give some recent results on homogeneous solutions of the generalized Cauchy-Riemann equations, but just in dimension 4. The dimension 4 is much easier than the general case due to the fact that the symmetry group spin 4 is just the product of 2 SU2. Its complexification is the product of 2 SL2. So in this case, it's quite easy to describe complex finite dimensional reducible representations denoted by S plus minus. the defining representations for the first and second copy of SL2. These are the basic spinor representations for spin 4. Then any irreducible representation is of the form S to AB, defined as the tensor product of the 8th symmetric power of S plus and the bth symmetric power of S minus. Any such representation is uniquely determined with the label AB. And the main aim of this talk is to study polynomial solutions of the generalized Cauchy-Riemann equations in dimension 4 with values in the spinor space of type AB. So let us start with describing important invariant operators in this case. As we know, the first step of the Stein-Weis construction is to decompose this tensor product. It has 4 pieces with labels differing by plus or minus 1 from the given label AB. Here we use the fact that the defining representation C4 is the tensor product of the basic spinor representations and the Clebsch-Gordon rule for SL2. We denote by pi plus minus the projections onto the corresponding pieces of the decomposition, and by composing these projections with the gradient, we get 4 differential operators: nabla plus plus, nabla plus minus, minus plus, and minus minus. The operator nabla plus minus, for example, increases A and decreases B by 1. And we shall need also invariant polynomial operators, not just differential operators, and we get those by replacing the gradient with the complex variable z of C4. And then we get, by the same construction, 4 invariant polynomial operators, z plus plus, plus minus, minus plus, and minus minus. These are dual in some sense to the differential ones. Pardon? Invariant with respect to spin 4 or SL2 times SL2. It's the same. It's not, yeah, but it's invariant with respect to rotational invariant. Yeah. So in dimension 4, the generalized Cauchy-Riemann equations is the homogeneous system for the Stein-Weis gradients nabla plus minus, minus plus, minus minus. And we are interested in homogeneous solutions. So let us denote by MABK the space of harmonic polynomials of degree k satisfying this system of equations. In this connection, just let us remark that solutions of the generalized Cauchy-Riemann equations are always harmonic, except for the trivial case when the values are just complex numbers. So, and then it is possible to prove that this space of homogeneous solutions forms an irreducible module with the label k plus a, k plus b. And what is interesting is that analogous result is not true for higher Dirac operators in general. For higher Dirac operators, the spaces of homogeneous solutions are very complicated, and in general they are highly reducible. And the last result I want to explain is the Fisher decomposition for any spin. The Fisher decomposition, this result is sometimes called also separation of variables. This is simply an irreducible decomposition of the space PAB of polynomials, in our case in dimension 4, which have values in the spinor space of type AB. And the spin S case includes the cases AB for which this equality holds, and the Fisher decompositions are well known for spin 0, 1/2, and 1, even in any dimension. For spin 3/2, we described the Fisher decomposition, but only in dimension 4 quite recently. Let me explain or describe the Fisher decomposition for spin 0. It's the classical harmonic Fisher decomposition or separation of variables for scalar-valued polynomials. In this case, we consider just complex-valued polynomials, and this space decomposes into irreducible pieces of the following form, namely this space MK00 is nothing else than the space of spherical harmonics of degree k, and it is multiplied by some power of R2, and R2 is just the square of the norm of the vector variable of R4. And this is invariant, polynomial invariant, and the dual operator is just the Laplace operator. And recently we have succeeded in describing the Fisher decomposition for any spin. Well, let us recall the notation. The spinor space SAB of type AB is defined in this way. P to AB is the space of all polynomials in R4, spinor valued of type AB, and this space MABK is the space of homogeneous solutions of generalized Cauchy-Riemann equations, K homogeneous. The Laplace operator we need just for the scalar or complex valued polynomials, and these operators Z minus plus, Z plus minus, Z plus plus are polynomial invariant operators dual to the invariant differential operators from the generalized Cauchy-Riemann equations. Then we have for any AB the following decomposition, and it contains pieces of the following form. Namely, we have the space of homogeneous solutions with a fixed degree of homogeneity and with fixed type, multiplied with some power of R2, and also with some power of Z plus minus or Z minus plus. And the last term means just that the operator Z plus plus embeds into this decomposition for the given spin or type AB, the polynomials of spin less by 1. So using this decomposition inductively, you can get easily the corresponding Fisher decomposition for any spin. Let me finish with the conjecture. We believe that analogous results for solutions of generalized Cauchy-Riemann equations hold true for any spin and in any dimension. So that's it. Thank you very much for your attention.